Hello everyone, my name is Yawei, and in this part of the tutorial, I will cover the topic of machine learned motion prediction for self-driving. Here is the agenda for this section. I will start with explaining what is motion prediction and why it is difficult. Then I will give you an overview of different approaches that has been explored in the research community. Last but not least, I will show you how you can train and test your own machine learned motion predictor using our open source library, L5Kit. First, what is motion prediction? It's predicting agents' future behavior in a dynamic and multi-agent environment. The agents here will refer to the traffic participants in real-world driving, such as vehicle, pedestrian, and cyclist. And an accurate motion prediction is vital for safe, comfortable, and efficient motion planning in downstream. For example, it is important to know whether to yield to a vehicle if they are going to cut in front of our AV. Or another example, when would be the best time for our AV to merge into a traffic? And to solve motion prediction, it requires an understanding of both the static and dynamic world context, such as an observation of other agents. So on the input side, we usually use sensor data plus perception output, illustrated here with a bird's eye view of a LiDAR point cloud. As you can see in the figure, the yellow bounding boxes are the detected agents using our perception system, and we need to predict their future behavior. On the other hand, road network information in HD maps is an important prior for prediction. For instance, the agent is more likely to follow its current lane on a strict road, or in case when agents approach red traffic light intersection, stop lines on the map can help the model to learn when to stop. And given this input, the goal of our motion prediction module is to predict how other agents are going to behave in the next few seconds. And it is a challenging task, and I will explain why in the next slide. So there are two key challenges. On the one side, it is challenging due to the highly uncertain of possible future in real-world driving. So the future might unroll in many different ways. One simple example is shown here. We have a vehicle approaches an intersection, and there's no evidence about whether it's going to continue going straight or make a right turn. So we need to build a system that is able to capture the multimodality in motion prediction. The second challenge is the fact that every actor is not really independent. So there's a lot of interactions between different actors, and the fact that one interaction might trigger a train of change in behavior across time. One simple example, we see two vehicles reaching an intersection with no sign of braking. Without interaction reasoning, these two vehicles are likely to collide with each other. So it is critical that our prediction system is able to exchange the information between actors and make more informed inference, such as the vehicle on the left is more likely to yield. And knowing the difficulty in motion prediction, let me show you some exciting work that tries to tackle this problem by leveraging recent advances in machine learning techniques. The first work is called IntentNet, and unlike traditional engineering stack for self-driving, where you separate perception and prediction into different modules, they propose to do perception and prediction jointly using shared representation. It has the advantage of avoiding information loss between modules, because when engineers handcrafted this interface between modules, those interfaces typically only pass information that engineers consider important, which can be suboptimal. It also has the advantage of reducing vehicle reaction time due to less compute and produce richer representation thanks to the joint optimization. And here it shows the overview of this approach. On the input side, we use a history of LiDAR sweeps, which are vectorized into a bird's eye view tensor and pass through a 2D CoverNet to extract features. And on the other hand, they also use map by rasterizing it into a bird's eye view image and extract features using another 2D CoverNet. And finally, the map features are concatenated together with a LiDAR feature before passing through the decoder. And on the output side, it predicts a detection score, a sequence of future waypoint regressions, and a multi-class classification over high-level intentions such as stop, lane change, or making a turn. And by adding this intention output, it allows the planner not only reason about occupancy, but also about semantics, which are very important for helping motion planning in downstream. And they show that this multitask model achieves better accuracy than the traditional modular approach while saving computation, and which is critical for real-time applications such as self-driving. The second approach is called Multipath, and instead of using raw sensor data, this approach leverages the perception system to pre-process the raw sensor data and produce a top-down view image by rasterizing the geometry of the perceived agents as well as the map in a multi-channel bird's-eye view raster. And this mid-level representation reduces sample complexity and allows the network to automatically infer relevant features. And another key difference is it tries to predict a mixture of Gaussian trajectory instead of single MAP trajectory, and tries to solve this multimodality problem in motion prediction. So it works as follows. Based on a top-down view raster image, as you see on the top left, the CoverNet ejects mid-level feature that encode the state of individual agents. And then for each agent, they crop an egocentric view of the mid-level feature and predict the probability over a fixed set of k predefined anchor trajectory. And finally, for each anchor, the model regresses the offset from the anchor states, as well as the uncertainty distribution for each future time step. So this approach is efficient. It requires only single forward inference pass to obtain this multi-model future distribution, which is quite important for real-time application like self-driving. Here is the example result for this method. As you can see on the left, Multipath method is able to predict different future trajectory at intersection with uncertainty eclipse. The trajectory probability are encoded in a color map, as you can see to the right. And the second picture, it shows that the Multipath can also predict future lane changes. As you see, it tries to nudge around the car in front. And the result shows that the benefits of Multipath over single MAP trajectory in capturing possible future outcomes and achieving more accurate prediction. And also it's efficient compared to sampling-based approach. It requires only a single feed-forward inference pass. And also the output is parametric. It allows a compact communication. Another way of modeling multimodality is performing multi-class classification over trajectory set. This has an advantage of easily incorporating prior knowledge into the trajectory set. For example, we can generate kinematically feasible trajectory sets based on current vehicle state. Examples are shown in the figure, where different sets of trajectories are used at different vehicle speed. The downside of this approach is that the number of trajectories needed to ensure coverage of all possible trajectories is quite large. More recently, some works propose to use vectorized representation to try to address some of the issues that we observe in raster representation. So compared with raster image, vector representation is less computation and memory intensive for high structured data like HD map. And also you can do one-to-one mapping between continuous trajectories and the vector set, which avoids the quantization artifacts in rasterization process. Last but not least, CoverNet is not really good at modeling long-term structure environment because they're made of small kernels and you need many layers for the information to propagate. So in a related work using vector representation called VectorNet, they propose to represent the HD map and agent trajectories using vectorized polylines. Just as you see in the figure, the crosswalk is simplified as polygon, link boundary as well as the agent history is simplified as polylines. And then they design a hierarchical graph neural network containing a local subgraph to gather information for each polyline. And then they have their global interaction graph in order to exchange information among polylines and to model the interactions between them. So this global interaction graph is implemented as a self-attention transformer layer. And finally, they have two losses. One is the L1 loss for trajectory prediction, and another is map completion loss to force the model to complete map features, and it can help with the prediction. And compared with the CoverNet-based approach, which uses the raster image, the VectorNet has significantly better performance in prediction in terms of final displacement error, and it uses a small fraction of the model parameters and 10x less compute, which is a quite exciting result. To summarize, here are the challenges that still remain unsolved in machine learned motion prediction. First is interpretability. Machine learned motion prediction has very poor interpretability, which poses a problem for validation and safety. And another problem is how to reliably capture model uncertainty as well as multimodality in an efficient way and avoid issues like mode collapse. Last but not least, is still an active research area about how to model agent interaction so that we can get realistic motion prediction at scene level. Okay, now let's jump into a hands-on session to implement a simple machine learned motion prediction model using our open source library, L5Kit. In L5Kit, we have a notebook for both train and test machine learned prediction, and I'm going to go through the key part of the code, and you can find the full notebook by clicking the link provided here. The first thing you want to do is to initialize a model, and you can select a common CoverNet backbone like ResNet50. And we also need to provide additional parameters to control how many future steps you want to predict and which loss function you would like to use. And after that, you can just train for a number of steps using our standard forward and backwards paths implemented based on PyTorch. And we also provide notebook for you to evaluate your trained motion prediction model. The first thing you need to do is to load the model. And you also have the option to use one of our pre-trained model available in L5Kit. Finally, you can run the evaluation loop and you can choose which matrix you would like to use for evaluating the model. And in L5Kit, we have the implementation of list of matrix for you. And here is an example result of evaluating our prediction model using evaluation notebook in L5Kit. And here I'm plotting the average displacement error for 3 models across prediction horizon. The models are trained with different portions of our 1000-hour prediction dataset, which is publicly available. As you can see, the prediction error reduces with more training data. And it shows a nice feature of machine learned model that you can improve model performance by adding more training data. Besides the quantitative evaluation result, you also have the option to visualize the scene to get some qualitative examples and do manual inspection. You can see here 3 examples by running one of our pre-trained model. Here we predict the motions for all the agents in the scene. As you can see, the prediction results is very accurate. And these pre-trained models are available with our notebook, so you can use them straight away if you want to skip training. I hope by far you have learned what is machine learned motion prediction and how you can implement it easily using our L5Kit. Thank you for your attention.